So let's talk about one of the biggest challenges in computing, scaling. We're going to break down how you can take a massive computational job, nearly double your horsepower, and, get this, do it all without having to rewrite a single line of your code.
I want to start with a question that honestly sounds a little too good to be true. What if you could get that massive performance boost just by changing one little thing? It sounds like a trick question, right? Well, stick around, because the tools to do this are very real.
Okay, so first things first, why do we even need to think about scaling beyond a single GPU? I mean, these things are already absolute beasts. But the truth is, for the really big problems, we're talking cutting-edge AI, complex scientific simulations, massive data analytics, one just isn't going to cut it. When we talk about scaling, there are really two main reasons you'd want to do it. The first is what we call strong scaling. This is all about speed. You've got a problem, maybe it's a weather forecast that takes 2 days to run, but you need the answer in a few hours, so you throw more GPUs at it to just crush that runtime. Then, you've got weak scaling. This is about size. Your dataset or your simulation is just physically too big to fit in the memory of one machine, so you add more GPUs to get more capacity, letting you tackle problems you couldn't even attempt before.
So you need that multi-GPU power. Traditionally, that meant getting time on some big remote supercomputer. But what if you could have that kind of power right there in your lab, or even sitting right on your desk? What if you could have your own personal, shareable cluster?
And this is what that looks like. You're seeing two DGX Spark units literally stacked one on top of the other. They're connected with this super fast 200 gigabit per second cable that creates a private network just between them. Then, another cable plugs the whole thing into your main company network. And here's the key part. This isn't just your machine. It becomes a shared resource that you and your whole team can log into and run jobs on. It's a real collaborative powerhouse.
All right, the hardware's all set up. But is it a nightmare to use? How easy is it to actually take advantage of all that power? Let's walk through a really quick demo that shows just how surprisingly simple this is.
So for our test, we're going to do a huge 40,000 by 40,000 matrix multiplication. That's a serious task, but just look at the code on the screen. It looks like normal Python. You don't see any of that complicated MPI stuff. No manual commands telling it how to split the data. It's written just like you would for a single computer.
So how do we scale it from one machine to two? This is the best part. You ready? First, we run the code on one node, just by setting a parameter, nodes equals 1. Then, to use two nodes, we don't touch the code. We just go to the command line and change that 1 to a 2. That's it. Seriously, that's the entire process.
And here's the payoff. Look at this. On a single node, that massive calculation took 9 seconds. Pretty fast. But by just changing that one number and running the exact same code on two nodes, the time drops to just 5 seconds. We got a huge speed up, and we didn't have to become distributed computing experts to do it.
Okay, I know what you're thinking. That feels a little bit like magic. How on earth did the system know how to split up the problem and manage the data between two machines when we didn't tell it anything? Let's pull back the curtain and look at the secret sauce that makes this all happen.
The key to all this is a technology called Legate. You can think of it like this super intelligent layer that runs underneath the libraries you're already using, like cuPyNumeric. It's a runtime system that came out of Stanford, and its entire job is to take care of all the messy, complicated stuff about parallel computing so you don't have to.
So Legate basically has two superpowers. First, it looks at your normal everyday code while it's running and automatically finds ways to chop up the problem and run it in parallel. Second, it handles all the data management, figuring out what data needs to go where, moving it between the machines, and bringing it all back together at the end. This is a total game changer. It means you get to focus on your actual problem, the science, the data, and you let Legate worry about the logistics.
Okay, this all sounds amazing, but if you're actually thinking about putting a mini supercomputer on your desk, you've probably got some very real, very practical questions. So let's tackle a couple of the big ones.
First up, the one everybody asks. You've got two high-performance machines pumping out a lot of heat, sitting right on top of each other. Isn't that just asking for a meltdown?
And the simple answer is no. This wasn't an accident or an afterthought. The DGX Spark was literally engineered from the ground up to work in this stacked setup. The entire cooling system is designed for it, so you can run them at full power, no problem.
Okay, next question. Performance. When you're moving all that data back and forth for a giant calculation,
isn't the connection between the two machines going to become a huge bottleneck and slow everything down anyway?
That's a great question, and the solution is a really smart mix of hardware and software. First, that cable connecting them is just blazing fast. Second, the software is clever. It overlaps the communication and the computation. So while the GPUs are crunching numbers on one piece of data, the next piece is already being sent over. It hides the delay. And finally, it uses cool tech like RDMA, which lets the GPUs talk directly to each other's memory, bypassing the CPU, which is way faster.
So let's zoom out for our final section here, because this is about more than just solving the problems you have today. Having a desktop cluster like this is really about preparing for tomorrow.
Think of this DGX Spark setup as a stepping stone. You're getting to develop on the latest architecture right at your desk. And because the programming experience is exactly the same, the code you write in Perfect here can be moved almost seamlessly to giant data center systems. Your work isn't stuck on your desk. It's portable. It's ready to scale up to a true supercomputer when you are. It's a platform that grows with your ambitions.
And that really brings us to the whole point of all this. All of this amazing technology, the hardware, the software, the fast connections, it's all designed to do one thing: get out of your way, to make scaling simple. So the real question isn't about the tech anymore, it's about you. If adding more power really was as easy as changing a single number, what problems could you solve? What bigger questions could you finally go out and answer?